Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the live streaming platform, the system that captures a broadcaster's video, encodes it, and delivers it to millions of viewers around the world in real time. We'll cover how platforms like Twitch, YouTube Live, and TikTok handle ingest, transcoding, packaging, CDN delivery, adaptive playback, and real-time chat. Whether you're preparing for a senior engineering interview or building video infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the live streaming platform, the system that lets a broadcaster send video to millions of viewers around the world in real time. If you have ever watched a live stream on Twitch, YouTube Live, TikTok, or a sports broadcast and wondered how the video gets captured, encoded, packaged, distributed, and played back with minimal delay while millions of chat messages fly by, this video is for you. We will walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FAANG interview or building video infrastructure, let's get into it. Here is the core problem. A content creator hits the Go Live button and expects their video to reach a global audience instantly, in high quality, without buffering or crashes. But behind the scenes, live streaming is one of the hardest distribution problems in system design. A single broadcaster can upload a high bitrate stream that must be transcoded into multiple resolutions and bitrates. Viewers are on different devices, networks, and continents. Some have fiber, others have congested mobile networks. Chat messages need to arrive in order and be synchronized with the video. Latency must be low enough for interactivity but not so low that quality collapses. Recordings and DVR must be available. Monetization and moderation systems must run in parallel. The platform must handle all of this at scale, with no single point of failure, and without bankrupting the company on bandwidth and transcoding costs. Let's walk through the functional requirements. First, the platform must ingest live video from broadcasters using standard protocols like RTMP, SRT, or WebRTC, and accept audio and video streams in common codecs. Second, it must transcode the source stream into an adaptive bitrate ladder, for example 1080p, 720p, 480p, and 360p, so every viewer can receive the best quality their network can handle. Third, it must package the video into delivery formats such as HLS or DASH, generate manifest files, and push segments to a content delivery network. Fourth, it must provide low-latency playback across web, mobile, smart TV, and set-top box players, with support for DVR, rewind, and catch-up. Fifth, it must include a real-time chat system, presence and viewer counts, moderation, and spam detection. These 5 capabilities form the backbone of any production-grade live streaming platform. Now the non-functional requirements. Latency is the headline concern. The delay from the broadcaster's camera to the viewer's screen must be predictable. Whether the target is standard HLS at 30 seconds, low-latency HLS at 5 to 10 seconds, or WebRTC sub-second. Scalability is critical because a single popular stream can spike from 0 to millions of concurrent viewers in minutes. Availability must be extremely high. If the platform goes down during a major event, the reputation damage is enormous. Quality of experience must be maintained across devices and networks, which means intelligent bitrate adaptation and fast recovery from packet loss. Cost efficiency matters because transcoding and CDN egress are expensive, so caching, multi-CDN failover, and edge optimization are essential. Finally, security and compliance are non-negotiable because the platform handles copyrighted content, user-generated chat, and payment data. Here is the high-level system architecture. On the left, the broadcaster sends a live stream over RTMP or SRT into an ingest service that authenticates the stream key and routes it to a pool of transcoding workers. The transcoding cluster produces multiple renditions and passes them to a segment packager, which slices the video into HLS segments and writes a master playlist. The packaged segments and playlists are pushed to a distributed origin storage system, and then cached at thousands of CDN edge locations around the world. Viewers request the playlist from the edge, download segments adaptively based on their bandwidth, and play them back in a player that handles buffering, bitrate switching, and error recovery. A parallel path handles real-time chat. Chat messages flow through a gateway and presence service into a publish-subscribe system, with moderation and bot detection running in the stream. Analytics and recording services consume the same media pipeline to produce replays and business metrics. The key metrics to memorize: cold time to first frame, the delay from a viewer clicking play to the first video frame appearing. End-to-end latency, the total delay from camera to screen. Rebuffering ratio, the percentage of playback time spent buffering. Concurrent viewers, the number of people watching a given stream at once. Bitrate adaptation accuracy, how well the player picks the right quality level for current network conditions. Chat latency, the time for a message to travel from sender to all recipients. Stream health and ingest frame drops, which measure whether the broadcaster's upload is stable. Transcoding cost per stream hour and CDN egress cost per gigabyte, because live streaming economics depend heavily on these two. These metrics tell you whether the system is fast, smooth, and affordable. Let's trace the end-to-end user journey. A gamer opens the broadcaster dashboard and clicks Go Live. The platform validates her stream key and starts an RTMP ingest session on a healthy ingest server. The ingest server forwards the stream to the transcoding cluster, which generates multiple renditions. The packager produces HLS segments and playlists, and an edge CDN is pre-warmed with the first few segments. A viewer in another country opens the stream page, the player fetches the master playlist, and adaptive bitrate logic begins playing at the lowest quality to minimize startup time. As the viewer's network stabilizes, the player steps up to higher bit rates. The viewer sends a chat message, which flows through the chat gateway and appears on other viewers' screens within a second. The broadcaster sees the viewer count rise, moderates a comment, and continues streaming while the recording service saves the entire session for later replay. The core models and algorithms. An ingest session represents a single broadcaster upload, identified by stream key, with state transitions like starting, live, reconnecting, and ended. The media pipeline model defines how the source stream is decoded, scaled, re-encoded, and packaged into segments and playlists. An adaptive bitrate ladder defines the set of resolutions, bitrates, and frame rates produced for each source. A playlist manifests map segment URLs to time ranges and is refreshed by the player on every target duration. The chat room model groups viewers into a channel and uses presence and heartbeat to track who is currently connected. Moderation and rate-limiting algorithms keep chat usable. The cache invalidation model decides when CDN edges should fetch new playlists and when segments can be served stale. The fundamental trade-off is latency versus reliability. Shorter segments reduce latency, but increase rebuffering risk and playlist request overhead. Now the low-level design deep dive. The ingest service is stateless behind a load balancer that routes by stream key hash to a sticky ingest node. That node writes the stream to a short-term buffer and forwards it to transcoding workers over a reliable internal protocol. Transcoding workers run on GPU or CPU pools depending on codec and cost, with autoscaling based on queue depth. Each worker writes segments to a distributed object store with strong consistency for the latest playlist. The origin storage serves as the CDN upstream and supports range requests, pre-signed URLs, and origin shielding. The player refreshes the media playlist every target duration, picks the next segment based on a throughput estimate and buffer level, and switches renditions when network conditions change. For chat, the gateway assigns a viewer to a shard, publishes messages through a fan-out queue, and delivers ordered messages over WebSocket or server-sent events. Recording and analytics are implemented as consumers on the same media and chat pipelines, so they do not block the live path. Key takeaways for your interview. First, live streaming is fundamentally a distributed caching and delivery problem, so emphasize ingest, transcoding, packaging, origin, and CDN working together. Second, always separate the real-time path from the recording and analytics paths to protect live latency. Third, latency is not a single number. Explain the trade-offs between standard HLS, low-latency HLS, and WebRTC for different use cases. Fourth, adaptive bitrate and player-side buffering are the primary mechanisms for quality of experience, so be ready to discuss how the player selects and switches bitrates. Fifth, chat is a real-time messaging system layered on top of video and must be designed for fan-out, ordering, and moderation independently. If you can walk through this architecture with these 5 points, you will signal strong senior-level design thinking. That's it for the live streaming platform. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the live streaming platform. We covered the full picture from RTMP ingest and adaptive bitrate transcoding, through HLS packaging, CDN edge delivery, player bitrate adaptation, and real-time chat architecture. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.